All right, so a little bit of history about this lesson. This is actually the lesson that I created when I interviewed for my position here at OBU. I'm kind of fond of this because I think it's a really, really cool application of calculus in business. And it's not something we have time to really get too much involved in, but I want you to see that there's more than what we've done. All right? The other thing about this that's interesting that I would encourage you to check out at some point in your future is that this comes from a perspective, if you've heard of him before, of Dave Ramsey. Do you guys know who Dave Ramsey is? I'm seeing some nods. So Dave Ramsey is a big part of my family. It is the reason that neither of my adultish children, the ones that are your age, live on campus because I won't let them borrow money to do it. So really, really big proponent of what he preaches, if you will. So I want to show you an example of integrals in action because we haven't really seen any really good applications of integrals. We don't have time for it, right? So I want to show you a really cool application. So I want you to imagine 50 years from now, you've led a good life and you've worked really hard and you've tried to save money where you could. But as you near retirement, you find yourself wondering, will I really have enough to retire? Is there some way I could have done better? How could I have projected better? What might your 70-ish year old self tell your 20-ish year old self today? So I would like for you to take a look at these antiderivatives. Many of you are still working through them in my office on gateway exams. Some of you are completed. They should be ones that are on your paper that you can fill in. So go ahead and fill those in as a remembrance. We're going to use at least 2 or 3 of them that are up here in our lesson today. So I want you to have that as a reference point. Integrals of constants, power rules, 1 over x, e to the x, e to the ax, and b to the x. And then, of course, we have constant multiplier rules and sum and difference rules. So jot those down. Guys. I kind of want to ask, do you guys remember these? But I'm fearful that some of you might not. So don't want an honest answer. So everybody's just going to say yes, okay? Do you remember these? Yes. Yes, of course you do. Thank you so much. These are the ones we've been working on. They're the ones you just took a test on as well. Right? Yeah. All right, so we're going to do an example. You've got one in your notes. 7 plus x to the 7 plus 7 e to the x plus e to the 7x plus 1 over 7x. Kind of like sevens.
Are we doing it together?
How about write down what you think you can remember on the pieces of it, and then we'll confirm it together. Would that work?
Yeah.
Yeah, all right. Get the pieces down that you know. We'll double check it. All right, what's the derivative of 7? 7x. How about x to the 7th? X to the 8th divided by 8. How about 7 e to the x? Oh man, e to the x is so friendly. How about e to the 7x? You guys are doing awesome. And the last one's the one that keeps tripping everybody up on their gateway. So somebody... You're like, I got this one now. Yeah. All right, plus c, indeed. 1/7 natural log absolute value x plus c. Okay, so that's just a refresher reminding you of all the pieces that we've done before. And we're ready to get started with what's really going on. You ready? All right. Oh, this is one more refresher, so sorry. Fundamental theorem of calculus. So the fundamental theorem of calculus tells us how we do an antiderivative with definite limits of integration, right? We take the antiderivative, capital F of x, and then we evaluated at the upper limit b, we plug b in, and then we evaluated at the lower limit a, we plug a in, and we subtract them. And we're going to be using this today. Okay, and let's practice using it on one example. Right here. So, first thing we need to do is just what we did on the last example. We'll do this one together. What is the antiderivative of 3x to the 4th? 3x to the 5th divided by 5. And how about 5e to the 0.4x? Lovely. Nope, not the natural log on this one because it is base e. Yep, so it looks like that. Or you can put 0.4. All right, this is just not working. There we go. We would put plus c, but I have definite limits of integration, so I don't really need it here. I'm going to evaluate this at the limits of integration 3 and 0. Okay, what that really means, we're going to go ahead and write it out longhand, is that we plug the 3 in. And we get that value. And then we plug the 0 in. Okay, so if somebody would grab, actually, if all of you would grab your calculator and evaluate this for me. In any of the ways that we've done it, you can use function integration. We're going to talk about that a little bit later if you've forgotten it. You can evaluate through a table. You can just flat out plug the values in straight in the regular screen. I don't care how you do it. But let's get a value for this together. For just part of it or for all of it? Because my answer for all of it looks different than that.
I got 116.7980.
I have 104.299.
Okay, everybody double check. This is what it should be. I have 80 written down when I created this lesson. I did it in 2 decimals, but we'll go with 3 if you'd like. 116.799. So everybody, you do as well. We should be getting this. Everybody good? Okay. So we're going to be using this fundamental theorem of calculus in a moment as well. Okay, so everything that I've shown you so far, you've known how to do. Because you probably you need to put the original function in there. You put the antiderivative in there. Yeah. Okay. Everything I've shown you so far, you've seen and you know how to do. We haven't done anything new, so this has been a review so far. The next component that I'm going to show you is something you haven't seen before. Oh, yes, Nan? What's that? Okay, did you put both pieces in?
Yeah. I get each one of these.
Okay, this is subtraction, and this is subtraction of a negative, so that would have been addition.
Yeah.
Is it maybe not addition? Because that looks like subtraction.
Okay.
I bet that's what's wrong.
Okay.
Double check it.
Okay.
Okay. This is actually in section 6.2 of your book. It's the future value of a continuous income stream. That's the title of it. And I'm just going to present it the way your book does. It says to suppose that an income stream, right, like your pay income, okay, in this case the income that you would be putting into an investment account, flows continuous into an interest-bearing account at a rate of R of T dollars per year, where T is measured in years, and the account returns an interest at the annual rate of 100% compounded continuously. The future value at the end of capital T years is given by this equation. So FV stands for future value. We have an integral from 0 to capital T. T is just how long you're going to invest the money for. R of T is the amount of money going into the account every year. E to the R, that little r is your interest rate. Capital T, again, is the length of time you're leaving it there minus T. Okay, the smaller t is the interest that's incurring over time. There's the time over which it's incurring. All right, so we're going to actually create the situation that's going to answer some of the question that we started with. What would your 70-ish-year-old self say to your 20-ish-year-old self? Every week, you spend $5 at the vending machine. Or Starbucks. I feel like I should change my example. I don't even think 5 sounds like a right number anymore. I think it's probably far more than that for most of you, spending on your different places you go. But we're going to go with 5. You know it's a waste of money, but what else can you really do with $5? Well, what if you invested it? Would it really amount to anything? What if it were $10 a week? If you were to invest that $5 a week or that $10 a week, how much would you have at retirement? That's the question we're going to actually explore. If I put in $5 a week, which is something that you guys could all do, right? You could, if you chose to do that. What would that look like? So we're going to take the $5 a week question first. So let's assume you invested $5 a week. How much would this amount to in a year? How would you figure that out? How many weeks are in a year? That's a good question. Do you guys know? Oh, good. 52. So this would be $260. $260 in a given year. Okay. Fair enough. That's R of T. Okay, so far so good, right? R of T is 260. So let's talk a little bit about the stock market. According to financial guru Dave Ramsey, the stock market is still the best place to invest your money. The long-term track record for mutual funds is still good, about 14%. So if you decided to follow Dave's advice and invested in a mutual fund with a solid track record of 14%, this 14% would be the R in your future value equation. So your R would equal 0.14. If you don't like 14%, you can rerun this with whatever percent you want. In fact, we're going to after a little bit. If you feel like 14% is ridiculous, that's just ridiculous. That never happens. I have some accounts that get really close to that, actually. It's not ridiculous. So let's see what happens. As you project into the future and you plan to retire at 70, we're pretending you're 20. I know some of you are older and some of you are younger than that, but just pretend for a moment you're 20 and you're going to retire at 70. How long would you invest for? 50 years, right? 70 minus 20 would be 50 years. That's capital T. Easy questions so far, right? Just looking at the context of what's happening. So using those pieces, we can create that future value equation. If you flip back to the page before, it's the one that looked like, whoops, there it was here. We just created R of T. What was it? 260. We know what the little r is. What is it? 0.14. We know what the capital T is, which is in 2 locations. It is 50. And we're going to write that equation down. So I'm going to flip back to my screen where I have space. So my future value is the integral from 0 to 50 of 260 e to the 50. No. It was r first, wasn't it? 0.14. And then 50 minus t dt. Okay. We did a section at the very last time we were together in 5.9 that was use substitution, and it was everybody's favorite. I mean, right? So this actually is a use substitution problem. So I'd like to show you how to do it as a reminder. So this is like a review class too, right? Yeah, absolutely. So we're going to take a look at what happens when we do this from a use substitution perspective, because it's a little bit different than the e to the x rule, just because of the way it's set up. So the first thing I'm going to do is I'm just going to distribute the exponent out, just because it's easier to kind of to look at. If I multiplied 0.14 times 50, what do I get? You guys know? What is it?
7.
It's 7. It's 7. So I'm just distributing this piece through like this. It's 7. So then I have 7 minus 0.14t dt. Everybody good with that? That's algebra, right? So the u substitution that I need is exactly that exponent, 7 minus 0.14t. I realize it's got t in it instead of x. I think you guys can handle that. It's just going to be a derivative with respect to t. So this is du on the left, and I'll have dt on the right to compensate for that dt. Okay? So what is the derivative of 7 minus 0.14t? It's negative 0.14. Remember, derivatives, not antiderivatives there. The derivative there is just the constant in front of the t. And then dt, exactly. Now, I recognize I don't really have a 0.14 in the equation, right on the baseline, if you will, down here. So when we did this in class, we talked about the fact that we could actually divide that 0.14 to the other side. You guys remember that? So when I'm coming over to my problem, it's an integral. I'm leaving the 0 and the 50 off for the moment. I can't remember if we did that in class or not. I think you did a couple of them like that, but I'm just going to leave it off for a moment. I'm going to have that 260, and I'm dividing by negative 0.14, and now it's e to the u du. Because the dt here at the end is being replaced by the du and the over negative 0.14. Okay? Now, we like e to the x rules, right? The derivative of e to the x is e to the x, and the antiderivative of e to the x is e to the x. It's lovely. So the antiderivative of what I have here is actually this same function. And yeah, it would have a plus c, but I'm going to put values in, right? The 0 and the 50 here in a moment. I can't put the 0 and the 50 in for u, though. Why? Because I need to change them back into t. 0 and 50 were input values for t, not u. Are y'all with me? So I need to change this back into t's. So this is 260 divided by negative 0.14. Maybe you have a value for that that's simplified, I don't know. And then we have e to the 7 minus 0.14t that we are going to evaluate at 50 and 0. Any questions to that point? All right, so we're actually going to plug in 50, like we did just a moment ago, into this equation. So it's going to look like, 260 divided by 0.14, e to the 7 minus 0.14 times 50. Minus 260 over negative 0.14, e to the 7 minus 0.14 times 0.
I think there's a negative in the first, where it says 260 divided by, does that mean to be a negative?
Oh, you mean I left it off here? Yes? Yes, they did. Thank you. Whoops. There. Perfect. So grab your calculator. Plug that in. What number did you get, Eric? You want to read me some numbers?
2,334,727
exactly right. $2,034,747.29. That is correct. That is what that is. So let's think about what really happened then. I know you're writing still, so let me pause. How much money did you actually invest? How much money did you invest each year? $260 a year, right? For how many years? 50. Could you find out for me how much money you put total into that account? $13,000 is the right number. You invested $260 a year for a total of $13,000. That's a lot of money. You could buy a pretty nice car for $13,000. You could, right? Yeah, you could. But at the end, instead of a car that is not so very nice any longer, you have $2,034,747.29. That's a pretty good trade-off. All with that one Starbucks coffee a week. Or the vending machine. It's $1.50 downstairs for a soda. Don't ask me how I know. It is. Do you guys want $2 million? Chloe does. Do I do this?
Yeah.
I invest. Yeah, I do. All right, technology. Now, you are trying to describe this to your parents because I'm pretty sure you're going to be pretty much like, that's pretty exciting. I'd like to have $2 million. You're going to go home and you're going to tell mom and dad. And as soon as you use the words calculus and antiderivative in your conversation, you get vacant stares. So to simplify things, you decide you will use a calculator to find the above values just to ensure your parents there's no funny math going on. After all, the calculator is always right. So I'll remind you how to do this. I know some of your calculators do this differently. So some of you have a notation in your calculator where it looks like this.
You want to show?
No, it's okay. I'll just write it up here. And then it has a box here, and it has a D and a box here. Okay? So either of these two. Okay, so your expression. I would like for you to enter the expression before we took the antiderivative. So I'd like for you to put, even without those blue pieces, I would like for you to put this without the limits of integration in there. Let's try that again. That. So in Y1 in your calculator, I'd like for you to enter 260e to the point 14, parenthesis 50 minus t, end parenthesis. You might, depending on your calculator, have to do, oops, I don't want to use that to write with, e caret parenthesis like this, 0.14, and then another parenthesis 50 minus t. Of course, with the 260 in front. Okay. That's what it should look like in your calculator. Okay, everybody got that in Y1? Fabulous. Okay. Then you have to enter into your regular screen your calculator. So exit out of the graphing part, back into the regular screen, and you're going to choose Math 9. Under Math 9, there's one of two different versions. Either your version will come up with this FNINT, or it will come up with this notation down here. If it's the one that's in my blue circle, it matches what's on the other screen. 0 on the bottom, 50 on the top. Y1 goes right here, right? 0, 50, and then there's an X right there. That blue is terrible. I should really change colors. Let's try that one. If not, then you can use the one I have. Yes, Janssen? Math 9. Yep, it's under Math 9. Are you there? Okay. Was there any funny math going on, Laura? No, there's no funny math. Oh my goodness. All right, once you put that in and I want you to hit enter, do you still get $2,034,747.29? Yes, you do. You really, really do. So I'm going to write that number down one more time to let it have sink in there. $2,034,747.29. Okay, but let's be real. You don't spend $5 a week at Starbucks or at the vending machine or at the Chick-fil-A or the whatever. You spend hundreds, don't you?
I spend 50 a week.
I believe you. I'm pretty sure that my oldest son has frittered away every bit of money he's made work we get Buffalo Wild Wings on food. Pretty sure it's true. So let's take a look at this. We're just going to change it from $5 a week to $10 a week. I mean, that we're just going to that one little change, $10 a week. Okay? See what happens. What if you invested $10 a week instead? Okay. So in a given year, what would you have invested then? $520. So we're just going to do the calculations all again with the 260 at the beginning changing to 520. So our integral from 0 to 50 of 520 e to the 0.14, and it was 50 minus t dt. And we're just going to do math 9. So what'd you get?
4,069,494.58.
Which looks conspicuously like twice as much, doesn't it? It's really close to twice as much. And it should make sense because we doubled our amount that we entered a week, right? It is. Yeah, it is. It looks a little funny because the numbers are a little weird. But yeah, it's twice as much. And the reason it's twice as much is because the 520 is twice as much as the 260. But the thing is that doubling the amount that I put in a week is not really what makes the biggest difference. What would make the biggest difference is if somehow we could actually get the interest rate to be higher. So I want to show you that the interest rate increasing is a significantly different value in what's going on. So assume again, we're going to go back to the $5 a week. Okay, we're going back to that situation. And instead of doing a 14% interest rate, we're going to do a 16% interest rate. So in terms of what we put into the calculator, what's changing is the 0.14 to 0.16. So I still have 0 to 50, $260, e to the 0.16, and then I have 50 minus t dt. Okay, so how huge is huge?
4,842,431.73.
And you still got to use that other $5 a week at Starbucks, right? Okay, so I wanted to show you by these two examples that they don't equally affect things, right? Your input that you have into the account has a direct impact. Double the input, double the output. But the interest rate doesn't work that way. And that's another reason why when you do invest things, you should keep up with what you're actually getting with whoever you're working with. So once a year, we go and we see our mutual fund guy and we talk over our accounts and we make changes if and when they're necessary. Yes, Katie?
So is there like an equation of some sort that can calculate for changing interest rates? I don't want
How interest rates changes? We're just using an average interest rate over the long term. And a mutual fund broker, I mean, someone who's doing what they would do, would actually be able to tell you over the length of this, this investment, they have made 10% or 12% or 20% or whatever over the life of the fund. Yep. Okay. Now, the thing is, people don't generally keep their investments constant throughout their life. If you invested $5 a week right now, that doesn't mean necessarily that next year you could not change it, right? Those things fluctuate. So we're going to take a look at an example of how something could fluctuate. As you consider your options, you realize that while you may not have much to invest now, you plan to have more in the future. I hope you have planned to have more in the future. Do you have plans for that? Yeah? I have plans for that too. I have plans for having more in the future. That would be great. So instead of investing $5 a week forever, you plan to increase your investment by $2 a week each year. Okay, so let's think about this thing. So this year, I'm going to invest $5 a week. But next year, 2020, I'm going to invest $7 a week. And then next year in 2021, I'm going to invest $9 a week. Okay, so just it's increasing a little bit over time. I hardly feel it because it doesn't really change that much. Are you with me? Okay, the investment just changes very slightly. So I'm going to show you what would happen with your R of T. So your R of T equation for this year was 260, right? But if you increase it $2 a week, how much would that increase in a given year? 2 times 52, which is 104. Yeah, 104. $104 additional next year times T. Because you want to do this for year 1, you add a 104. And for year 2, you're going to add another 104. And for year 3, you're going to add another 104. Does that make sense? Here's the thing. This R of T equation, we need Math 9 to do because you don't know how else to do it. All right? There are methods, but they're not what we're dealing with. Okay, so your calculator is going to be really necessary here. So let's take this equation and we're going to do our future value at 14%. So again, 0 to 50. I have 260, and then this parenthesis needs to be around here. 260 plus 104t, all that's in parenthesis. E to the 0.14, back to our 14% interest rate. And then I have 50 minus t. You'll notice all my comparisons compare back to the very first quantity because I'm trying to give you a comparison of how things change without changing two things at the same time. All right, grab calculator. Math 9.
That is 5,789,000.
Mine's bigger. Yep. Double check your parentheses. Remember too when you're doing this that this is E and you've got the caret like this. I could have an answer wrong on my paper. That's what I have.
Yep.
No worries. 7 million. Who says sign me up? I like the 7 million number. I'm all about that one. That looks really good. 7,811,168.14. And guys, do you realize that if I'm even half wrong, that's still $3.5 million? I could be off by 50%. You've done a lot of money, wouldn't you? Oh my goodness. Oh my goodness. I'd like to show you an interesting piece. This is not directly related to anything that you've probably seen before, but I want to show you, because I showed you before that you invested $13,000, which is not very much considering you got $2 million output, right? $14,000 for a $2 million output. I want to show you how much you invest with this one, but it's a little bit harder to see how it works, so it's going to take me just a little bit to walk you through it, okay? The amount you contribute in this particular scenario increased $104 every year. Remember that? So year number 1, you had 260. And year number 2, you'd have 260 plus 104, which would be 364. And year number 3, you'd have 468. And then we'd have 572, and so on. And if we did this for 50 years, on the 50th year, we would actually invest $7,540. But let's be honest, if you got to year 50, I hope that you don't still owe money on a car and a house. You really shouldn't. You've been living there forever, right? You have some money at that point. Probably you're traveling. I hope you're traveling. That's what my in-laws are doing right now, traveling everywhere because they just retired. The common difference, the amount that we add every time, is 104. Agree? Every year it's an additional $104 more than the previous year. There's an arithmetic summation formula. Again, you would have no reason to have necessarily seen this before, but I'm going to show you right now. And it tells you how you can add lots of numbers together and find their sum when they're arithmetically like this. The way that you do that, it's 1/2 times n times a1, this is just your first term, plus AN, and this is your last term. So we're going to identify what our N, our A1, and our last term A50 are on my next slide.
Wish I had this last year.
What in the world? Oh, I didn't write it using the summation formula. We know that. Oh, I left it off. Okay. What is N? The number of years. It's 50, right? We said we were going to invest for 50 years. What is A1? A1, the amount that we invest the first year. 260. And what is A50? That is the amount we invest the 50th year. It was a lot, right?
7,000.
Yeah, 7,540. So we can actually find out S sub 50, how much we would be receiving or earning, not earning, but how much we would have put in during those 50 years by taking 1/2 times N is 50. And then I would have the first term 260 plus the last term 7,540. I promise I'm not going to ask you to calculate this on your test. That's not the point. I just am curious so you can see, okay? So what do you get when you add this all, multiply this all together? Yeah, $195,000. You can buy a nice house for that. You can. Nice house for $195,000. So in this scenario, I didn't invest $13,000 and get $2 million when I retired. Instead, I invested $195,000, significantly more, no question. But I retired with how much? $7,811,168.14. So what will it be? $5 a week at the vending machine, or be a millionaire at age 70? Up to you.